Alright guys, good morning. So I'm going to go ahead and walk you through the review worksheet. I also have up here where you can find it in your notebook if you'd rather just work on your own. So I'll just kind of work through all these problems, and you guys got a worksheet you can do, and then it'll be due on Monday in class. So let's go ahead and begin here. We have two functions, h and g, and what this is what's called a composition. It's where you're plugging one function into another function. Okay, so we have our h function, right? And our g function. Matter of fact, I think the way I originally did this was like the following. So I'm going to start by writing the function that's on the inside out first. So we have g of x. And then we have this function on the outside, h of x. Now I'm going to write h of x, but whenever I do, I'm just going to leave some blanks there where the x is located. So notice I've just rewritten the two functions, and the h function, which is the outside function, I've rewritten it where the x's have blanks instead. And what I'm going to do is I'm going to be plugging the g function into the h function. So what that's going to look like then is the following. Now, you can leave your answer like this, but it's pretty easy to go ahead and simplify this one. Sometimes they're kind of a pain to simplify. This one's pretty easy. We're just going to distribute and combine like terms. So the final answer would be 8x plus 12. And that's what we call a composite function. Okay? All right, let's move on to the next one. We have another one here. So in this case, we're taking our inside function, which is g, but this time we're plugging something into the g function as well. I'm going to be replacing the variable, in this case it's a, with the number 3. So I'm plugging in 3 for a. And what that gives me is g of 3 is 6. Now, we want to figure out what is f of g of 3, so I'm going to take my outside function. Once again, I'm going to write underneath of that with blanks. A squared plus 1. And once again, we're going to just drop this function inside. And in this case, all I have is a number now. So I'm going to plug that in as well. And so f of g of 3 is 36 plus 1, which is 37. Okay. Move on to number 2. It says graph the polynomial function. All right. This stuff gets pretty detailed. The first thing, there's really two things that we need to know, actually. It's not that bad. Is we can find out where it touches the x-axis, and then we need to figure out what the end behavior is. Okay? So let's go ahead and figure out where it touches the x-axis first. Well, where it touches the x-axis, that's when y equals 0. Right? And so what we're going to do then is we're going to set each one of these factors equal to 0, and we're going to solve. So negative x equals 0, x plus 3 equals 0, and x minus 1 squared equals 0. So this one obviously is just 0. That's one of our x-intercepts, or also known as roots. This one, if you subtract 3 on both sides, you end up with x equals -3. That's another one of our roots. This one, if you square root both sides, you just get this, and then adding 1 on both sides, we get 1. So I've got 3 places where this polynomial function touches the x-axis. It touches the x-axis at 0, -3, and also at 1. Okay, so that's one thing that we want to be aware of. Now we get to figure out the end behavior. Okay, so let's jump to a new screen here for that. Negative x, I got to remember it first. All right, so we have -x times x plus 3 times x minus 1 squared equals y. Okay, so I'm going to do this the long way, but then I'm going to show you guys the short way, and then I would encourage you just to use the short way. Okay, but the short way doesn't really make a whole lot of sense until you really understand the long way. All right, so first of all, we're going to take this x value here and we're going to distribute that inside like that. That's going to give me -x squared minus 3x. And then I'm also going to multiply that thing out there. That's x squared minus 2x plus 1. Okay? Now I'm going to multiply this whole polynomial by that whole polynomial. Okay? Now I'm not going to show my work for that. I'm just going to show you the answer really quick. Alright, so once again, you could ignore the work. I'm not going to worry about that. I'm going to trust you guys know how to multiply polynomials for now. But this is what we get by multiplying all those things out. Okay? Now, here's the shortcut so you don't have to do that. First of all, I'm trying to figure out what the end behavior is. If you guys don't know what that means, is that the end behavior of a function is where it goes up on both ends or down on both ends or something like that at the end of the function. So functions can either go up forever or down forever on either side of the graph, and I just want to know what's the end behavior, what's it doing. There could also be horizontal asymptotes, in which case it gets flat. So that would look something like that at the end behavior. But when you're dealing with polynomials, that doesn't happen, so we can ignore it. So the question now is what's happening on the right? Is the graph going up or down? What's happening on the left? Is the graph going up or down? Well, long story short, what we found in our studies in the past is that it's the first term that really kind of determines what the end behavior is going to be. Okay? So we actually don't need to do any of this work right here. All of this is ignorable. We don't really care about it. Why is that? I'll show you. I'm going to black that out because we don't care about it. All right. We don't care about it because all you have to do to get this first term, which is all you really need to know the end behavior, is multiply the first term of each factor. So x times x times x with a negative. And this x is being squared, so it's really going to be an x squared. So it's really just going to be x times x squared, which is -x to the 4th. Okay, so we don't need to do all that crazy polynomial work. Now what? Now what do we do? Well, we need to figure out what's going on at the end behavior. In other words, what's happening as x goes out to infinity. I'm going to use this is your guys' favorite. I know you guys don't like this stuff. But what's happening here to the function as x goes to positive infinity? Well, and also we want to know what's happening as it goes to negative infinity. Okay, well, infinity means we're just getting bigger and bigger and bigger, right? So just for the heck of it, what we could do is we could just plug in a pretty big number. For instance, let's say 100. So if I'm going to positive infinity, let's plug in 100 for x and see what's happening here. Okay, 100 to the 4th power is going to be, I think it would be this, but the exact value doesn't matter, and that negative's there. So let's ask ourselves then, as x gets bigger and bigger and bigger, the output, the y value, is becoming what? Super negative, right? In other words, as x gets bigger and bigger and bigger, y just becomes more and more negative. So it's approaching negative infinity. So as x approaches positive infinity, y approaches negative infinity. Let's see what happens if I plug in something down here, though. Here we're going to negative infinity. That means I'm plugging in smaller and smaller numbers like maybe a negative 100. So let's say if I plug in a negative 100 now. Well, the funny thing is when you raise a number to an even power, you get the same thing. So this answer is going to come out to be exactly the same thing as the other one I got. So it's also going to negative infinity. So now let's interpret that a little bit. That means as x goes to infinity, that means I'm going to the right. As I go to the right, the y value is going to negative infinity. That means y is going down. So as my graph goes to the right, the y values go down. Here means as x goes to the left, y is going down. So what this means is that on the left side of my graph is going down, and on the right side of my graph is going down. Okay. Another way that you can do this, instead of just figuring it out like this, if you want to just use a table to help you out, and knowing this, I gave you guys a little bit of a chart before. So suppose you guys have something that looks like this, right? For the problem we just had, it was negative x to the 4th, right? It was negative 1x to the 4th. Well, what we talked about there was that the n value can be even or odd, and the a value can be positive or negative. And it's always going to be one of these 4 things. If a is positive and n is even, then it's up on both ends. But if a is negative and the n is even, it's down on both ends. And that's what we had on the example that we were doing, because my a was negative and my n was even. Now when a is positive and n is odd, it's up on the right and down on the left. But when a is negative and n is odd, it's opposite, up on the left, down on the right. So that was the chart I had. But you can also, for me, I'm not good at memorizing stuff, so I figure it out by just plugging in numbers. But charts are nice because they're fast. So it's up to you on what strategy you use. But regardless of how you figure out what the end behavior is, what we have discovered from our study there is that it goes down on both sides. So we know that it's going down on this side, and it's also going down on this side. We're getting there. We have one more thing. Something else that we talked about was multiplicity. It's a little word we probably haven't heard in a while. And what we learned there is that even powers bounce, odd powers go through. And yes, I'm misspelling through. So notice here, for this root, 0, that came from this factor. That's x to the 1st power. That's an odd power. It's going to go through the x-axis. X plus 3 is also a 1st power. That's also an odd, and therefore this root, the graph will go through it as well. But this particular factor has an even power, and even powers bounce off of the x-axis. So I'll show you what that looks like. That's this one right here. So starting on the downside, it's going to come up, it's going to go through the root, it's going to come back down and go through that root, and it's going to swing back up and it's going to bounce off of the last root. It does not go through the x-axis. And so that's how we can graph a polynomial function. It may not be very precise, but it's close. So it's a three-step process. Step one, find your roots. That's what this work over here was. Step two, do the end behavior. That's what all this stuff was that we were talking about here. What's going on the right. Take each term, multiply them all together to get your first term, which tells us the end behavior. You can either figure it out by plugging in big numbers, or you can just use the chart, whatever you prefer. And then finally, we have to look for bounce points. Where does it bounce off of the x-axis and where does it go through the x-axis? After that, you should be able to connect the dots and get a pretty decent picture. So that's how you graph one. So if you're using the chart, it doesn't really have to be that long. It's actually pretty quick and easy. But there it is. So let's go ahead and we'll move on to the next question. Next question is kind of the same thing, but kind of different. It's asking us to do the opposite. Instead of giving us the equation and asking us to graph it, it's giving us the graph and asking us to find the equation. Okay? So, first off, let's go ahead and take a look at our roots. The roots are -4, 0, and 4. So if my roots are -4, 0, and 4, then my factors would be x plus 4, x, and x minus 4. But notice, we also need to concern ourselves with the multiplicity. Let me write this first. So now let's do the multiplicity. That's where we look for the bounce points. Which one of these roots is a place where the graph is bouncing off of the x-axis? Right there. This one goes through the x-axis, this one goes through, but it bounces here. And what that means is that that root, which was 0, which gives me a factor of x, has a multiplicity of an even number. So that means that the x has to be squared. It really could be any power. We don't know what power it is, but we do know it has to be even. And so right there, we almost have the entire equation. We have it bouncing off of 0, and we have our 3 roots. The one thing that we don't know is we don't know what's the number in the front. You know, like on the last problem we just did, there was a -1 in front of everything, right? But for us here, you know, what is it? It's kind of difficult to tell. Well, what we notice here, they give us the coordinates of a point. What we're going to do is we're going to plug in 1 for all the x's, and we're going to plug in 1.5 for the y. And by doing that, we can solve for a, and we'll have our final answer. So, last thing we need to do is plug in the point. So, let's do that. We have a, and we're plugging in 1 for x, and 1.5 for y. So that gives me a times 5 times 1 times -3 equals 1.5. Now this is -15, so I have -15a equals 1.5. And if I divide both sides by 15, what do we get? If I divide both sides by negative 15, we get a equals negative 0.1. All right? So my final answer then is I'm going to take this one, and now I'm just going to plug in what I got for a. I got negative 0.1, and then x plus 4, and then x squared, and then x minus 4 equals y. And so that would be the equation of that graph. It has the 3 roots that we want, negative 4, 4, and 0. It bounces at 0, so it has an even power. And I also have an appropriate coefficient in the front so that I end up with the point that it's going through right there. Notice, by the way, that I've got a negative 1, right? It's negative. And then I have x times x squared times x. If I multiply all these numbers in the front, I get x to the 4th, and it's a negative in the front. So it's negative 0.1 x to the 4th. Notice it's going down on both ends, just like the last graph was because of that. So that makes a lot of sense. Anyway, so here's your steps. Identify your roots, turn them into factors, get the multiplicity on there, plug in your point to figure out your a value. You have your equation. Okay, that's polynomials. Let's move along. We also need to know how to solve some equations, so let's do that. All right, so what I want to do is first I'm going to get this square root piece all by itself. So the first thing I'm going to do is get rid of the 3 by adding it to both sides. Now I need to get rid of the square root. The opposite of a square root is a square. So I'm going to square both sides. And when I do that, this square cancels that root, and I'm left with 81 equals 27x. Finally, I'm going to divide both sides by 27, and I'm going to get 3. Now, the problem tells us to check for extraneous solutions. That means it's possible that when we solve this, we could get a value for x that actually is illegal and not allowed. The reason for that is because square roots have a restricted domain. They can only have positive outcomes in here. So if we had anything that would give us a negative, it'd be no good. But as you guys can see, if I were to plug this in, we're going to be okay. But I'll just show you the whole thing. 27 times 3 is 81. And the square root of 81 is 9. And negative 3 and 9 makes 6. So we check everything out okay. It didn't give us a bogus outcome. So this is just checking my work for extraneous answers, but this is how you actually solve it over here. Get the square root piece by itself, and then square both sides. All right, moving along. Here's another one. More of the same thing, really. I want to get the square root by itself, so I'm going to add. Oh, wait, what is it asking for? Oh, it's not asking us to solve. It's actually asking us to graph, so that's a whole other deal. Okay. Fair enough, fair enough. Game changer then. We're not getting the square root by itself. A little bit of background first. Square root functions look like this. They start at 0 and they go up like this. It's like half of a parabola on its side, if you will. But our particular square root function has some transformations. First of all, you guys got to remember your transformation rules. Whenever you subtract 1 from the x, that will shift the graph to the right 1 space. That's a translation, right? And up here, this one's not being subtracted from the x. This is being subtracted from the whole function. So that's an outside change. And outside changes are vertical. So this is also a shift, but it shifts the graph down, since it's negative, 3 spaces. So what's happening here is my graph is getting shifted one space to the right and down 3 spaces. Now the 2, I really don't care too much about stretches and compressions. This would actually be a vertical stretch. It's an outside change. I'm not too concerned about that. But what I am concerned with is reflections. So watch out. If this were a negative in the front, that would flip our shape upside down so it looks like that. Okay, so beware. If it's negative, it flips your shape upside down. Okay, so in this case, my graph is being shifted to the right 1 space and down 3. So now it looks like this. And if you want to get picky, you could say, okay, well, it's a little bit taller looking now because it's being stretched by a factor of 2. But there you have it. So just before I abandon you guys to try some more on your own, I wanna give you guys a little chart for reflections here, because reflections can get a little weird. Okay. So we have, let's say I have this. I've got A on the outside and B on the inside. Reflections is what we're looking at here. If A is negative, then it flips the graph upside down, right? Well, actually, let's do positive A first. Let's say both A and B are positive. When A and B are positive, it just looks like this, normal, all right? But if the A is negative, then it flips it upside down so it looks like that, just so you know. Now, but what happens though if there's a negative in front of the x inside the square root? That means the b is negative. Well, that's a horizontal one. So if the a is positive, it's still upward like this, but a negative b will flip it so that it's going the other way. If they're both negative, then we're taking this shape, we're flipping it upside down and sideways, and that would look like this. So if you want to use that little chart to kind of help you know how to deal with your reflections, you can. So just to recap, so long as you know that typically they look like this, right? You're going to shift it to the left or right using this number. You're going to shift it up or down using this number. Shift what? Well, really you're shifting the whole graph, but I just kind of use my starting point as my anchor point. After that, you're going to use the signs in front of the x or outside in front of the square root to determine what direction it's opening. Okay? So that's how you graph a square root. Let's go ahead and take a look at cube roots. Cube roots are kind of the same. So cube roots, what they usually look like is the following. They look like this. That's what they normally look like. But once again, we have the same transformations to deal with here. So I'm going to rewrite this though, because sometimes when the constant's in the front, people get really confused. So I'm going to write -3 cube root of x plus 1, and I'm going to put the -2 in the back. Okay, so what do we have here? We have, that's a shift to the left 1 space. Remember, minus is moving it to the right, plus is moving it to the left. And this one is a shift down 2 spaces. Remember, when you have the outside changes, that's up and down changes, and negative means down, positive means up. So this point right here, since I have these transformations, is going to be moved to the left 1 space and down 2 spaces. So this point gets moved down to here. So my shape would now look something like this, but I'm not quite done yet because we have some reflections to deal with. Notice I've got a negative on the outside. Now that's a vertical reflection. So if you can just do this mentally, can you imagine what this shape would look like if I just flipped it around that point right there. If you can't, that's okay. I'll give you a chart. But what it would look like is it would look like this now. So that would be our final answer. And there you go. But I'll give you a chart for the reflections once again, because this one is a little bit different looking. But before I put the chart up, just to remind you once again, know what the basic shape of a cube function, cubic function looks like, cube root function looks like. It looks like this. Know how to shift it to the left and right, shift that middle point. And then don't forget to get your shape correct based on the reflections. So here's the chart for this one. Usually, when you have a cube root function, all right, when both a and b are positive, it just looks quote unquote normal like that. But if a is negative, that's a vertical reflection. It flips it upside down and it will look like this. If b is negative, just the b, that's going to flip it sideways and it's going to look like this. Notice that a sideways reflection looks almost the same, actually exactly the same, as a vertical reflection. And if they're both negative, well, if I take this, flip it sideways and upside down, we're actually just going to end up right back to where we were. So if they're both negative, it looks like the original function. Okay? So that's the reflections for cubic functions. Been a while since we did that. All right, next one, number 8. Let's go ahead and solve this. Solving exponential equations. We're going to get the exponential piece by itself. So the first thing I'm going to do is I'm going to minus 3. By the way, these are calculator questions. You would need a calculator to do these. Your cell phone should work fine. Next, to get the exponent piece by itself, you're going to divide both sides by -9. The negatives cancel, and I'm left with like 0.1111111. Okay. The next thing that we're going to do is we're going to log both sides. That's the real trick there. So we're going to log base 10 now. Log both sides. Why would we want to do that? Well, there's a log rule that tells us when you have the log of an argument and your argument has an exponent, you could take that exponent and move it to the front. And so that's going to change our expression into the following. b plus 8.9, our exponent's now in the front, of log 6 equals log of 0.1 with a bar over it, meaning it just keeps going. The next thing you would want to do, remember we're trying to get b by itself here, is I'm going to divide both sides by log 6 to cancel that out on the right side. Okay, so from here I'm going to need a little help from my calculator. I've got to figure out what is log of 0.1 divided by log of 6. So let's do that. Open up my calculator real quick. All right, so we're going to do log of 0.1. Now I'm going to put 0.1 a few times because it actually just keeps repeating. Divided by log of 6 equals -1.226. 3 decimals is probably good enough. And then finally, I'm just going to minus 8.9 on both sides. And once again, I'm just going to let my calculator do that for me. So minus 8.9. And I end up with negative 10.126. And there it is. So most of the first few steps are kind of cool. Just get rid of the non-exponent numbers. After that, you log both sides. After you log both sides, you slide the exponent to the front. Then you divide the log, get out your calculator, and finish the rest. Okay? Now they want us to graph an exponential function. Okay. Well, it kind of helps to know what exponential functions look like. They look like this for the most part, and they have horizontal asymptotes. Okay, so it's nice to be aware of what exponential functions look like before we begin. All right, so the first thing we're going to do to graph these is we're going to graph the horizontal asymptote. That would be this number, negative 2. Okay, next we're going to find the y-intercept. That is found by plugging in 0 for x. That gives us 1 point. And then after that, we're going to plug in any other point you want, really. Let's just do 2 points. We'll plug in 1 and negative 1. We're going to pick one number to the right of 0 and one number to the left. And that should be kind of sufficient to give us our shape of our graph and connect the dots. So first of all, we're going to plot our horizontal asymptotes at negative 2. So I'm going to go down 2, and I'm going to put a little dotted line. There's my horizontal asymptote. Step 1's done. Step 2, I'm going to find my y-intercept by plugging in 0 for x. So 4 times 2 to the 0 minus 2. Now, don't forget this. Anything to the 0 power equals 1. It does not equal 0. Kind of weird, but that's how it is. 4 times 1 is 4, and 4 take away 2 is 2. So my y-intercept is 2. So it touches the y-axis right there. Now I'm going to find 2 other points by plugging in 1 and negative 1. So here we go. That's 1 we'll do, and then we'll also plug in negative 1. All right, 2 to the first power is 2. 4 times 2 is 8. 8 take away 2 is 6. So when I plugged in 1, I got 6. So there's another point. 1 and 6. 2, 3, 4, 5, 6. So it's going to be up here somewhere. And then when I plug in the negative 1, for this, there's a few ways you could find out what 2 to the negative 1 is. First of all, you just put it in a calculator. You'll get 0.5. Or you can just remember that a negative exponent makes a reciprocal. 4 times a half is 2, and 2 minus 2 is 0. So when I plugged in negative 1, I got 0. So at negative 1, we're right here. Now, we've got 3 dots, and based on what we know about the shape of exponential functions, it should be up against the asymptote and swinging up this way to hit those 3 points. Now, be aware, I mean, they could be going this way, they could be going this way, they could be going this way, they could be doing lots of things, and that's why we get 3 points to kind of rule all those other possibilities out. Just make sure that it's getting flat against the asymptote, and it hits those 3 dots and has this general shape to it. Okay, that's how you graph an exponential function. Let's go ahead and continue on. All right, now we have a log function. We're going to be solving a log function. So I'm going to put parentheses around that real quick. The first thing that we want to do is get the log by itself. Now I want you guys also to be aware that this expression is different than this expression. In this case, if they have parentheses, that means the 2 is part of the inside of the log there. If they don't have parentheses, like in this case, that means only the negative 3x is the inside. The 2 is actually an outside number. So what we want to do is get the log by itself and get rid of the outside numbers first. So I've got log base 2 of negative 3x equals 1. Okay. The next thing we're going to do is this is a tricky one, we're going to exponentiate both sides. That means I'm going to take this and make it an exponent of this base here, which is 2. So 2 to the log base 2 of negative 3x. And whatever you do to one side, you do the other. So now this is going to become an exponent of the same base. So both of these become an exponent of 2. Now why do we do that? Well, there's a log rule. The log rule says this: anytime you have a raised to a power of log base a of x, it's kind of like these two just cancel each other out and you're just left with x, right? So in this case, the 2 cancels with the log 2 and we're just left with 3x. 2 to the first power is 2. Divide. Got your answer. Negative 2/3. It's always good with log equations as well to make sure that you don't end up with an extraneous solution. This piece here has to be greater than 0. So if we plug that in, log base 2 of negative 3, let's plug in our answer. You know, you don't have to show your work. You could just kind of do this mentally. But I'll work out the whole thing. Negative 3 times negative 2/3. Well, the 3's cancel and the negatives cancel, and you're left with 2. Log base 2 of 2. There's another log rule that says that whenever these bases match, it's just 1. So this is 1. So we're good. It worked. Now you don't have to work it all the way down like this. Just check mentally in your mind. If you plug in negative here, up here, the double negatives canceling up with a positive. So it is greater than 0 and we're good. That's pretty much all you needed to do. But let's go ahead and review before we move on. Get rid of outside numbers first. Exponentiate both sides. Solve for x. Okay? And make sure your answer is not bogus. Graphing logs. Graphing logs. All right. So fourth period, you guys had a little bit of a hard time with graphing logs. We didn't quite get to finish that lesson. So I'll show you how to do it today. This will be a great opportunity for us to kind of fill in a blank that you had. I'll also show you the way that I taught my classes, since you guys kind of got in a little bit different way. All right, so if you want to graph a log function, the first thing that you need to do is you need to find the domain restrictions. As I've already told you, this piece here has to be greater than 0. On the last problem, right? We said that. So that means that x plus 3 has to be greater than 0. So if I solve that for x, then I end up with the fact that x needs to be greater than negative 3. Now what that tells me is that tells me my next thing I need to do. That tells me where my vertical asymptote is. For those, in case you forgot, log functions look something like this. They look like exponential functions that are flipped on their side. They have a vertical asymptote. Okay, and the reason they look like that is because they're actually the inverse of an exponential function. So what this means is that since x always has to be greater than negative 3, there's an invisible barrier that our graph cannot cross. It can't be anywhere behind negative 3. So my vertical asymptote is at x equals negative 3. These are identical. So x has to be greater than negative 3, and that invisible barrier known as a vertical asymptote is therefore at negative 3. So for now then, I know this much. I know that I've got an invisible barrier here. And I know that my graph has to be greater than -3, so that means to the right of it. Now, log functions can look in one of 4 ways. They can go this way, like that. They could be flipped upside down if there's a reflection. They can also be reflected to the left or flipped upside down and reflected to the left. So they can go in one of 4 different directions. The way we're going to figure out what direction they are in is by just picking a few points and plugging them in. Okay, so step 3. Pick 2 x values in the domain to plug in. Okay, so notice that my domain is x is greater than -3. So what are 2 numbers that are greater than -3? There's a couple, okay? Let's go ahead and say, how about x equals -2? That's greater than -3. And how about, you guys are going to think I'm weird for saying this one, but how about x equals 7? All right. Now, why did I pick 7? Why not just -1? That's the next number, right? Log functions grow very slowly, so if you pick 2 x values that are really close together, you might not see the change very much, and you won't be able to tell what direction it's going. So you want to pick some x values that have a little bit of distance between each other. That way you can kind of see the change a little bit better. Okay. So what I'm going to do now is I'm going to plug those numbers in so I can get 2 more points to plot, and I should be able to find my graph that way. So here we go. I'm going to plug in -2. Let's do that one first. So -2 plus 3 is 1. Get out your calculators and just type log 1, see what you get. You should get 0. And so I get 2. So when I plugged in -2, I got 2. So there's 1 point. Now I'm going to plug in 7 and get another point. Oops. Log 10 is 1, and 1 plus 2 is 3. So now when I plug in 7, I get 3. So I've got 2 other points to graph now. So I've got -2, 2, which is here, and I have 7, 3. 1, 2, 3, 4, 5, 6, 7, and 3 would be somewhere like here. So as you guys can see, there's a gradual increase, not much. Like I said, they grow very slowly. So, but you can see that it is bending down this way, and so we can tell that our asymptote's going like this. So there's our graph. Okay. All right. I wonder if that's it. That's our last problem. So that was a lot of work, but there you guys have it. You guys have your worksheet that you're going to work on with the sub. Whatever you don't finish, you can go home and work on at home. The video will be on Google Classroom, so you're welcome to look it up and fast forward to a particular part if you need to watch the video again and get a little bit more help. Okay, so we'll see you guys on Monday, maybe, if not Tuesday.